Next, we're going to look at a couple more reactions of alkenes. Ozonolysis is a reaction where we take an alkene and we essentially cleave or break the pi bond and the sigma bond present. So that's what makes it kind of unique, because up until now our reactions have only been breaking the pi bond and the sigma bond was left intact. So this is the reaction of an alkene. In the first step, it reacts with ozone, which we'll look at ozone as a reagent. And in the second step, there is a reduction, and there's a variety of reagents that can perform the reduction. And what it does is it breaks the alkene into essentially two different fragments. And so this type of reaction where we break that sigma bond and the pi bond of the alkene is referred to as oxidative cleavage. And ozonolysis is just one type of oxidative cleavage reaction that you could have. And it's the only one that we're going to look at right now. So in step number 1 of the reaction, we use ozone, which is O3, and that is the structure of ozone. There is a difference of charges within that molecule. It's overall neutral, but one of the oxygens has a positive formal charge, and the other oxygen has a negative formal charge. And then in step 2, we use a reducing agent. Some common reducing agents that you could see are something like dimethyl sulfide, which is abbreviated DMS. What that is a sulfur with two methyl groups coming off of it. The sulfur has two lone pairs of electrons like oxygen would. You could see something like H2S, which basically looks like DMS, only there's two hydrogens bonded to the sulfur. And you could also see something like zinc in acetic acid. So zinc is a metal that can act as a reducing agent and get oxidized, and it would take place in acidic solution. So if you see something like zinc with HC2H3O2, that's acetic acid, and that just is a reducing agent that's being used in the second step. So when we're drawing the products of this ozonolysis reaction, what you want to imagine is that you draw a line down where the double bond is, right along that alkene, and imagine breaking it into two halves. So one side right here, and the other side right over here. And so we're going to get two products, and we could get two aldehydes, or we could get two ketones, or we can get a combination of aldehydes and ketones. And this depends what our starting alkene is. So in this example, notice coming off of carbon number 1, you have an R group, you have an alkyl group, and you have a hydrogen. So on that side, that's going to lead to the formation of an aldehyde when we cleave that sigma and pi bond. So the aldehyde has a hydrogen right here directly bonded to the carbonyl carbon. And in our second fragment on carbon number 2, notice on our example here, we have another one that has a hydrogen bonded and an R group. So in this example, our second fragment formed was also an aldehyde. So you could have a combination, and it's just going to depend upon what your starting material is. And if there is a hydrogen that's directly bonded to that carbonyl carbon, or is it two R groups, or is it formaldehyde, which formaldehyde is the simplest aldehyde, where you have two hydrogens directly bonded to the carbonyl. Now let's look at the reagent that we're going to be using in the ozonolysis reaction, which the primary reagent is ozone. It has the formula O3, and ozone has two resonance structures that we can draw, and we can push the arrows to move from one resonance structure to the other. So if we start with the electrons on the oxygen with a negative formal charge, and we move them in between the one with the positive, and then we take the electrons and move them to the outer oxygen, we would end up with the second resonance structure, which kind of looks like a mirror image to the first. And ozone is the same ozone you might have heard about that's found in the upper atmosphere. So what happens is oxygen gas that's in the atmosphere gets bombarded with ultraviolet light. The ozone layer in the atmosphere is what protects us from harmful UV radiation, so when we get a sunburn, for example. Now, ozone is rather unstable and it cannot be stored in a gas cylinder. So when it's going to be used in the lab, it has to be produced as you need it and as you're going to use it up. And so its instability is what allows us to undergo this ozonolysis reaction, because it can undergo a rearrangement to form essentially a more stable version of itself, as we'll see in the mechanism. And then in the second step, we break down that more stable intermediate using the reducing agent to essentially cleave the bonds and separate it into the two fragments. You're going to come across many different reducing agents in organic chemistry. Recall that the definition of a reducing agent is something that causes reduction in another species. So the reducing agent itself actually gets oxidized in one way or another, and it causes reduction. So when we add the word agent at the end, it's what it does to something else. So a reducing agent causes something else to get reduced, just like an oxidizing agent causes something else to get oxidized. So that's opposite from our Leo Ger definitions, where we said loss is oxidation, so loss of electrons, and gain of electrons is reduction. So if something is a reducing agent, it is actually the thing that's getting oxidized. So that was just a little bit of a reminder from general chemistry about, the terminology that's used. As we said a couple slides ago, some common reducing agents to be familiar with: dimethyl sulfide, which is DMS, hydrogen sulfide, and a lot of metals, zinc is just an example of one, are common reducing agents. So zinc in acidic solution is a reducing agent. The first step of the ozonolysis mechanism is a concerted step where a lot of electrons move at once in concert, and it's also a syn attack, meaning it's happening on the same side. So initially what we have is our electrophilic alkene will attack this outer oxygen here, allowing the electrons between the two oxygens to shift to the oxygen with the positive formal charge. So then that gets rid of that formal charge on that oxygen. You can think about it like the driving force. And then at the same time, instead of forming a carbocation, the electrons on the oxygen with a negative formal charge go back and attack. And so we have this ring that's formed, this 5-membered intermediate, where we essentially have lost our pi bond that's in between our two carbon atoms. That was broken, but we formed two new single bonds in its place. So we have a new bond between carbon and that oxygen, and between carbon and that oxygen. And notice our 3 oxygens in a row, they are just singly bonded to one another now, and there's no formal charges. Also, I want to point out that initially, notice starting off, we had 2 methyl groups on the left-hand side of our alkene, and then 1 methyl group on the right-hand side, and we have a hydrogen here. So when we undergo the cleavage of this reaction, we're going to end up with a ketone for one fragment and an aldehyde for the other. So we'll get a mixture of ketones and aldehydes as our products. This first intermediate that we formed is a rather unstable intermediate. It's called the Melozanide Intermediate. And this guy wants to undergo rearrangement into the more stable Ozonide Intermediate. You might remember that hydrogen peroxide contains a peroxide bond. A peroxide bond is that single oxygen-oxygen bond that you see. And those are weak. They like to break, and they usually break and form radicals, which is why I use that fishhook arrow as an example. Not always will they, but just commonly. And so this OO bond is very unstable, which is why the Melozanide Intermediate, which has 2 oxygen-oxygen single bonds within it, is going to break down and rearrange. So that's the driving force for this thing breaking apart. And the next step is those weak oxygen-oxygen single bonds that we have. So the first step is for this to break up into fragments, and it really doesn't matter what direction you start. So if we take our sigma bond in between our two carbons, and we break that, which we normally don't break a sigma bond, but we're going to break one here because this is going to rearrange and reform. We'll push the electrons in between this carbon and this oxygen, and that'll form a double bond there. And then next, we're going to break this bond between oxygen and oxygen, and those electrons are going to go to the oxygen. I could have broke this around the other direction, going towards the left, and my two fragments would have just been a little bit different, but it still would have rearranged in the same way afterwards. So now we have our carbon-oxygen double bond right here, which is from those electrons that we drew in blue, forming that double bond there. And then we have a negative charge, negative formal charge on our oxygen on the second fragment from the electrons that are in between the two oxygens that were cleaved. So we have these two fragments, and there's an electrophilic center and a nucleophilic center, and these fragments are going to recombine. And their goal is to form a more stable intermediate, which is going to be the ozonide intermediate. So our negative charged oxygen is going to act as a nucleophile and attack this partial positive electrophilic center where we have the carbon that's bonded to the carbonyl. So we have this attacking here, and then immediately what will happen is our electrons that are in between our oxygen and our electrophilic carbon center will go back and attack this electrophilic center. So we can imagine that that carbon will be partially positive because it's bonded to an oxygen, which is electronegative. Now, it's common practice to draw the electrons coming from the pi bond between that carbon and oxygen. But if you really want to think about it like they're coming first up to the oxygen and then attacking, because the real bond is going to be formed between the oxygen and this carbon center. So this isn't technically correct to draw it that way, but it's the best way to think about it because we're going to have a bond that's formed between oxygen and that carbon. So the correct way is to draw from the pi bond to the electrophilic center, but just keep in mind that the bond we're forming is going to go from here to here. So then when we rearrange now, you can count around the ring. Just count the atoms in this new ring that we're forming. So I'm just going to start counting anywhere. 1, 2, 3, 4 is the carbon of the carbonyl, and 5 is the oxygen. So we have 5 members in this new ring that we're forming. So here's our new 5-membered intermediate. This would be what I called position number 1, and then I went 2, 3, 4, 5. So you can see how those pieces match back up. Off of position 1, we had those 2 methyl groups, and we still got those. And off of position number 4, which was our carbonyl carbon, we have a hydrogen and a methyl group, and we still have that there. So now in the new ozonide intermediate, there is one peroxide bond between what we have labeled as 2 and 3 that can be broken. That's still unstable, but it's not as unstable as the first intermediate that was formed. The second step, we are not going to go through the individual steps showing the reduction. This is the actual oxidative cleavage part where we're doing the breaking into fragments. So you would pick any one of those reducing agents, and you could see any one of them in the homework or anything, so be aware that they exist. Any one of those reagents will perform this final step where it breaks it apart. So these are essentially our reducing agents. And so when they themselves they will get oxidized. So for example, if we were to use something like dimethyl sulfide, and that was going to get oxidized and cause reduction of our ozonide intermediate, we would form a product such as DMSO. This is dimethyl sulfoxide. So recall that this is the sulfoxide functional group. And so it was oxidized in the process. This is just a side product. You don't have to show that. So our 2 fragments then that we form are our aldehyde, in this case, and our ketone. And an easy way to look at your starting material, So if we just draw our alkene over one more time, and it's all marked up at the top, so we don't want to look at that one. Just draw a bond breaking down the middle, and then look at each side and put an oxygen here and an oxygen here, and then redraw them separately. So that's a quick way to get at drawing the products. So this could take you immediately to here if you weren't writing out the whole mechanism and you were just doing products and reactants. So you can see your two sides. You've got one right here, that would be your ketone, and then you've got another molecule over here, and that would be your aldehyde side. Now we're going to look at our first radical reaction. A radical reaction is a chain reaction that will involve free radical intermediates, and it has the same three steps: an initiation step, some propagation steps, and then a final termination step. So the initiation step is what gets it going. The propagation steps are it moving and propagating throughout, and a termination step is where two radicals come together and essentially eliminate the free radicals. When we are showing mechanisms involving radical reactions, we use something called fishhook notation. So radicals are essentially an unpaired electron, and when they form, bonds break and one electron goes to one side and the other electron goes to the other. So they move individually instead of in pairs. So the fishhook arrows look like that, where we just are showing one side, versus our traditional curvy arrows where we have two heads on that. So we have a single head on the fishhook arrows versus the double head that you see that we normally use. So for example, HBr, if that was going to break apart and we were going to use fishhook arrows to form a hydrogen radical and a bromine radical, we would take that covalent bond between them and we would push one electron to the hydrogen and one electron to the bromine. As a result, we would form a hydrogen radical, so notice the one unpaired electron, and a bromine radical. So both of those have one unpaired electron, which makes them highly reactive. So there's something that will cause this to happen in the initiation step. We'll talk about what that would be. And once you form your radicals, then you start going through the propagation steps, where now radicals are forming more radicals and they're combining with other things to rip electrons off and form more radicals until something comes together and two radicals combine in a termination step, where now we don't have radicals floating around anymore. So radicals are highly reactive and they're going to want to react and rip electrons off of other things. In your body, you might have heard that free radicals are bad and we want to get rid of them. So we want to consume antioxidants. Well, that's because oxygen is essentially going to be the biggest cause of free radicals in the first place. And so that's bad to have that happening in your body. So we consume fruits and vegetables which contain antioxidants to get rid of them, to tie them up. The stability and structure of radicals should look rather familiar because it basically mirrors what we previously saw for carbocation stability and structure. So a radical would be on a carbon and it would be living in an unhybridized p orbital. It has just that one electron there that's unpaired up. And notice we have this planar structure, 120-degree bond angles, and the carbon is sp2 hybridized. So this is just what we saw for our carbocation, only we didn't have electrons, so our carbon had a positive charge. Well, here we just show that single dot representing that there's an unpaired electron on this carbon. And our radicals are stabilized in a similar fashion. As you go from primary to secondary to tertiary, we are increasing in the stability of that radical. And it depends upon how many alkyl groups are surrounding that carbon with the unhybridized p orbital on it. So all of these carbons that we have with the radical on them are all sp2 hybridized. So they all have one unhybridized p orbital where that electron is living. So how could we stabilize unhybridized p orbitals? Well, we could have alkyl groups surrounding that could push electron density back through induction. So this one has one R group that can push electron density back. The carbon is lacking electrons. It's got one that's unpaired with nothing else. So one alkyl group will do that once. If you have two alkyl groups, inductive effects will push back twice. And if you have a tertiary radical, inductive effects will push back in 3 locations. So having a tertiary radical is the most stabilizing effect for that unpaired electron. We previously looked at the addition of something like HBr or HCl across the double bond, and what we saw normally was that when we use something like HBr, the bromine got added to the most substituted side, and hydrogen got added to the least substituted side. That was called the Markovnikov addition. But what's interesting is if we use the same reagent HBr, but we perform the reaction in the presence of peroxides, so that's what this ROOR is representing as a peroxide, where maybe instead of hydrogen peroxide, which is HOOH, we could replace the hydrogens with any alkyl groups, really, or it could be just simple hydrogen peroxide. But what we get is the bromine gets added to the least substituted side instead. And so this would be considered an anti-Markovnikov addition because the group got put on the least substituted side of the alkene. So this reversal of the regioselectivity of this reaction is often called the peroxide effect. In fact, when we learned the hydrobromation oxidation reaction, what we saw there was that we had an alcohol placed on the least substituted side, and we also used peroxide in the second step for the oxidation there. So that could help you remember that these two reactions are both the anti-Markovnikov reactions, the BH3-THF reaction, and then this free radical addition of HBr, and they both contain peroxides in their set of reagents. So we're going to look at the mechanism of how this occurs, and it's totally different than what we saw for the mechanism of our just regular Markovnikov addition of a hydrogen halide. So our free radical addition of HBr, our mechanism is going to seem a little weird because we're going to be using those fishhook arrows, which represents the movement of just one electron instead of 2 at a time because it is a radical reaction. And so in our initiation step, something like UV light, which often people will just write E equals H nu. You might remember that H was Planck's constant and nu is the frequency, and those two multiplied together gives you the energy. Regardless, something that's high energy, such as UV light, can initiate the breakdown of peroxides to form radicals. So our peroxide will split and one electron will go to each side. And what we form then are 2 hydroxide radicals. This is our initiation. Step here. So this is how we've created our radicals. And so using something like electromagnetic radiation, and maybe in the form of UV light, is a common radical initiator. So now we have our radicals, and that radical, one of them, can react with our HBr reagent. And what it will do is it will abstract a hydrogen radical from the HBr in order to form water. So it's trying to react away that free electron that it has because it's unstable. So one electron from our hydrogen will combine with the one free electron from the hydroxide radical, but then the other electron has to stay with the Br. So we form a bromine radical, but we also formed water when the hydrogen radical combined with the hydroxide radical. So those 2 electrons came together to form that new bond. So this would be an example of a propagation step. Now our bromine radical is going to react with our alkene. So 1 pi electron from our alkene will combine with the bromine radical. Those will come together and form a single covalent bond. But then the other electron of our pi bond has to stay with the alkene. And we have 2 spots that we could place it. We could place it on the more substituted side or on the least substituted side. And when deciding, we would be choosing between a secondary radical versus a tertiary radical. So this reaction could go one of 2 ways. And we just talked about radical stability, and we said that the tertiary radical was more stable than a secondary or a primary radical, for example. So the intermediate that this reaction is going to go through is the one in which the radical is placed on the tertiary side because it's more stable. So instead of forming the secondary radical, we won't see that pathway happen. We won't form that. That means that the new bond to the bromine radical gets placed at the least substituted position. So notice where our halogen was added, because our radical is going to be on the more substituted tertiary side. So now the final step is to essentially terminate our radical reaction by combining our alkyl radical with a hydrogen radical in the reaction. So we have a combination of this hydrogen radical with our alkane radical that we have there going on, forming a new bond. And we can think about that like our termination step, which is ending the reaction and giving us our final product. And in our final product for the free radical addition, what we end up with is a halogen, in this case Br, on the least substituted side. So that's why this is referred to as an anti-Markovnikov reaction. The last reaction that we're going to look at, we're only going to talk about the products and reactants and not actually go through the mechanism because it's slightly confusing and it's not like a normal arrow pushing mechanism. But this is a reaction that you want to be aware of because it's used for all kinds of things that we use every single day. So this is called the hydrogenation reaction. And just like it sounds, it's adding hydrogen across the double bond. So if we have an alkene and we expose it to hydrogen, and we also have to include a metal catalyst that the hydrogen can adsorb to, we can undergo what is known as a catalytic hydrogenation. So the metal that is allowing the hydrogen to adsorb essentially acts as a catalyst. And a catalyst is something that will help speed up the reaction without being consumed itself. So the metal is important to have, and there's lots of different metals that you can use essentially that are unreactive, such as platinum or palladium. But the whole point of that is just to provide a surface for the hydrogen gas and the alkene to interact on. There's two types of catalysts that we would have talked about in general chemistry: heterogeneous catalyst and homogeneous catalyst. So a heterogeneous catalyst is when it's in a different phase as the reactants, and it's considered a homogeneous catalyst when the reactants and the catalysts are all in the same phase together. So if we peek at the potential energy diagram on the right, you have the energy of your reactants and the energy of your products. In this example, the products are lower in energy than the reactants, so we would say this reaction is exothermic, or the enthalpy is negative. But what I want to hone in on is what the catalyst does to the activation energy. So notice the height here of our activation energy for our uncatalyzed reaction in the green. A catalyst doesn't change the initial energy of the reactants or the final energy of the products, but what it does is provides a new pathway to lower the activation energy. And so it allows the reaction to occur faster due to that lowered activation energy, which is abbreviated E sub A. So that's all a catalyst does, is create less barriers and make it easier to clear the transition state by lowering the activation energy. So for the hydrogenation reaction, if we imagine that we have cyclohexene to start with, and we react with hydrogen gas, and we use platinum, which the PT over C means platinum plated over carbon. So the platinum is essentially the metal that's acting as the catalyst. But platinum is an expensive fine metal, so in order to not use a lot of it, it's plated onto carbon. And notice the products, the regioselectivity. This reaction is a syn addition when we undergo hydrogenation. Both of the hydrogens get added to the same side of the original double bond. And that's due to how the alkene interacts with the hydrogen that is adsorbed to the surface of the metal catalyst. So this is why we're not going to get into the whole mechanism of it, because it's more like a actual picture you would draw rather than an arrow pushing mechanism. But what it does is it essentially turns alkenes and later, as we'll see, even alkynes, back down into alkanes. It reduces them, so it's a reduction reaction, into alkanes. So the key player is the hydrogen, but it has to have that metal catalyst for it to work as well. And the hydrogens are added to the same side of the double bond. So we have syn additions. They're added to the same face. So some common catalysts that you could see, platinum over carbon, palladium over carbon, nickel over carbon. The point is, notice that there's a lot of variety of metals that are used to facilitate the interaction of the hydrogen gas with the alkene. In real life, you might have heard of hydrogenation when talking about oils or butters and stuff like that. If you have something that's an oil and it contains double bonds within it, so you could have a mono unsaturated fatty acid, which that's something that's found in like olive oil. You could have trans unsaturated fatty acids where the groups are on opposite sides of the double bonds. You could have polyunsaturated fatty acids where you have multiple double bonds. All of those can be hydrogenated and reduced down to their corresponding alkanes where they are considered to be fully saturated. So this alkane would be an example of something that we would say is fully saturated. Remember degrees of unsaturation. The alkene has 1 degree of unsaturation, so it's not fully saturated. But our alkanes, they have all the maximum hydrogens that they can hold, so that's why we say they're fully saturated. And that's where the name saturated fats come in, is because after you hydrogenate something, you essentially turn it into a fully saturated fat now, where those are usually going to be things like your butters, where they're solids, versus your things that have degrees of unsaturation are going to be more like your oils and stuff. So this is where hydrogenation kind of comes into play, as in a lot of food chemistry. So let's just go through a quick summary of all the alkene reactions we talked about. And there's a couple on here that I moved to a different chapter and we haven't talked about yet, so I want to cross those out. But if we start at the top here with ozone, we took an alkene and we cleaved the double bond and we got a mixture of either both ketones, both aldehydes, or one of each, depending upon our alkene that we started with. Next, we saw the hydrogenation reaction, where we had hydrogen gas, which is the important one, and then a variety of catalysts. You don't have to include all of them. Palladium over carbon, it could be platinum over carbon, for example, but that took us all the way down to an alkane. So that was our reduction reaction. Here we have aldehyde and ketones. Next, we used mercury 2 acetate, and in this one we have an alcohol, so that alcohol could change. Remember, the R group is actually going to be something like methanol, ethanol, propanol, butanol, that we actually have to include on the final product, but for now it's just showing R. That gave us an ether type product. And the second step after we did the mercury 2 acetate with the alcohol solvent, we used sodium borohydride to reduce it. And that was a Markovnikov addition, where our group ended up on the most substituted side. Next, we learned about hydroboration oxidation. That was a 2-step process also. First step used BH3, which is borane, in tetrahydrofuran. In step 2, we used hydrogen peroxide with sodium hydroxide. This was an anti-Markovnikov addition, where the hydroxyl group of the alcohol product that we formed ends up on the least substituted carbon of the alkene. This next reaction we actually did not cover, so you can see that this gives you carboxylic acids, but you can ignore this for now. This got moved to a later part. Following that, around the circle, we have our mercury 2 acetate with water as our solvent in our first step, and then our sodium borohydride in our next. So this is our Oxymercuration Demercuration. And on our most substituted carbon, we end up with a hydroxyl group, so we form an alcohol. This would be a Markovnikov addition. The next one here, this also got moved to a later chapter, this ozone peroxide one, so you don't have to know that diol that's formed. The one after that, we have our free radical addition of HBr. In this case, we ended up with a bromo group on the least substituted side. So this was another anti-Markovnikov addition that was done using hydrogen peroxide and HBr. Next, we have our hydrohalogenation, HX, where X is a halogen. So the identity of that halogen can change, but what we ended up with was a halogen added to the most substituted side. So that would be a Markovnikov addition. Next, we have just the plain old halogenation reaction. So X2 could be Br2Cl2, for example. Here we added that halogen across the double bond, and because it's the same, we ended up with a halogen on the least substituted side and the most substituted side. If the alkene was equally substituted, we still would just end up with it added across, one on each side. This next reaction, these next two are ones that we actually skipped and were moved to later ones. So this whole section of the summary you can ignore as well. We will talk about some of those when we do the alcohol chapter. So those are the reactions that we covered in the alkene section. So you're going to want to make sure that you can look at a set of products and reactants and predict missing reagents. And you can also look at reagents that are given to you and predict the products that are going to be formed. You also want to be sure that you can draw the mechanisms for the ones that we did mechanisms for and be able to push the arrows and draw the intermediates in between going from reactants to products and essentially understand what is going on throughout the process, going on throughout that reaction to get you from one step to another step. There are also a couple other subsets of reactions that we saw within the halogenation one. We did the halogenation with water as a competing nucleophile. We did the halogenation with an alcohol as a competing nucleophile. And we did the halogenation with something that was more nucleophilic, such as sodium chloride when we had Br2. So those three reactions essentially would fall under that halogenation, only we had a nucleophile or a solvent that could compete. And so that changed the identity of not having two of the same thing across the double bond, but having the halogen on the least substituted side, and then having either an OH group or an OR group or a chloride group on the more substituted side. So make sure you check back and look at those reactions as well.